The solution that we have for robot motion planning finds one way to go from the source to the destination, but there could be many ways to go there. For example, this red line or slightly better purple shortcut over here that take a shorter path to get there. So a more interesting question is to find the shortest path between the source and the destination. For example, in this picture, the shortest path could look something like this. And in particular, the shortest path has this property that you have to turn very tightly around the corner. So from here, we have to go to this corner, turn directly towards that corner, and so on. That's essentially, you can show that that's a property of the shortest path. But now the question is, how do we find this? So to solve this problem, first we can do everything that we've done in the previous solution to enlarge the obstacles, which would essentially turn the robot into a point robot. So we're just going to solve this problem for the point robot. As we discussed, the general problem can be reduced to this case anyways. So so we have this point robot and we want to find the shortest path. How do we do this? Okay, based on this observation that we have made, the shortest path between S and T is a polygonal path. The inner vertices of this path are the vertices of the obstacle as well as the bounding polygon, and the first and the last point are the source and the destination, or the source and the target. So therefore, the idea to build a short path is relatively simple. Just build a graph where you have an edge between every relevant endpoints, and then assign a weight, which is the distance, and then just use the shortest path in a graph, or in other words, turn this into a graph algorithm. The way we can connect this and connect two vertices is that two vertices are relevant, or is if they can see each other. In other words, once you connect them with a line segment, the line segment does not intersect anything. And that actually is the definition of a visibility graph. The visibility graph of the vertices of this polygonal scene encompasses the edges, where each edge connects two vertices that can see each other. The claim is that we can compute G is in n squared log n time. Okay. So an example of visibility graph here is going to be something like this. So from this vertex we can see all these vertices, from that vertex we can see all those vertices, and so on. And then we draw all of them on top of each other. So that's the visibility graph of this polygonal scene. So obviously you could see that in the worst case this could have n squared edges. For example, if the polygon is convex, then every pair of vertices can see each other, and that's essentially the maximum number of vertices you could have. So it's a complete graph. So you could have the visibility graph be a complete graph, so it could have n squared size in the worst case. So therefore, it's not surprising that it needs at least n squared time to be computed. But how can we compute it n squared log n time? The idea is to first compute the visible vertices from one point in n log n time. So in particular, from here we can compute all these edges in n log n time, n log n time, n log n time, etc. Since there are n edges in total, that would bring the time to n squared log n time. And that's what we're going to do next.